In September 2024, Dr. Elena Rodriguez watched in fascination as a seemingly impossible demonstration unfolded 400 kilometers above Earth. The International Space Station, humanity's greatest achievement in space construction, was about to receive an upgrade that would revolutionize space travel forever. A thin, nearly invisible thread extended from the station's hull, a 20-kilometer electrodynamic tether that interacted with Earth's magnetic field to generate thrust without consuming a single drop of rocket fuel. As electrical current flowed through the ultra-thin conductor, the Lorentz force pushed against the planet's magnetic field, slowly but steadily boosting the ISS's decaying orbit. Elena, a 33-year-old materials engineer at the International Space Elevator Consortium, had spent the last 8 years working toward this moment. The ISS tether demonstration was just the beginning of humanity's most audacious engineering project, building the first space elevator. The concept was elegantly simple, yet mind-bendingly complex. A cable extending from Earth's surface to beyond geosynchronous orbit, held in place by the planet's rotation and centrifugal force. Satellites, cargo, and eventually passengers could climb this cable into space at a fraction of the cost of rocket launches. What had been science fiction for over a century was finally becoming possible thanks to a revolutionary new material, single-crystal graphene. Elena's laboratory at the ISEC facility in Quito, Ecuador, housed the most advanced materials testing equipment on Earth. Here, she and her team of 200 researchers were perfecting the production of single-crystal graphene, a form of carbon 200 times stronger than steel, yet lighter than aluminum and more flexible than rubber. This material was strong enough to support its own weight across the 100,000-kilometer length required for a space elevator. The breakthrough had come in 2023 when researchers at Shanghai University successfully manufactured a continuous sheet of single-crystal graphene measuring 50 meters long with no defects. Elena's team had refined this process, developing techniques to produce graphene tethers at the industrial scale required for space elevator construction. But Elena knew the space elevator was just the ultimate goal. The real revolution was already beginning with shorter tethers that could transform how humanity operated in space. Companies like Percy Space in Spain were developing electrodynamic tethers that could provide propellantless propulsion for satellites. Instead of carrying heavy fuel, spacecraft could use long conducting cables to push against planetary magnetic fields for orbital maneuvers. The physics was based on principles discovered over 150 years ago. When a conductor moves through a magnetic field, it experiences a force perpendicular to both the motion and the field, the Lorentz force that drives every electric motor on Earth. In space, a current-carrying tether could use this force to speed up, slow down, or change orbital inclination without expending propellant. Elena's first major project had been developing tethers for the growing space debris crisis. With over 34,000 trackable objects cluttering Earth's orbital highways, something had to be done. Traditional rocket-powered debris removal was prohibitively expensive, but electrodynamic tethers offered an elegant solution. The European Space Agency had contracted Elena's consortium to develop the ET-PAC project, electrodynamic tether technology for passive consumable less deorbit kit. The system consisted of a 100-meter conducting tape that could be deployed from dead satellites. As the tether cut through Earth's magnetic field, it generated electrical current that created drag, gradually lowering the satellite's orbit until it burned up in the atmosphere. Early tests exceeded all expectations. A 3U CubeSat, equipped with Elena's 20-meter aluminum alloy tether, demonstrated orbital decay at an average rate of 2.3 kilometers per day at 800-kilometer altitude, reducing the satellite's orbital lifetime by over 70% compared to passive decay. The system operated with minimal power draw, averaging just 0.5 watts. But the real breakthrough came when Elena's team solved the deployment problem that had plagued previous tether missions. Space tethers had to be incredibly thin to minimize mass, often thinner than human hair, making them prone to tangling during deployment. Elena developed a multi-strand design with segments that could break away if tangled, combined with an AI-controlled deployment system that monitored tension and automatically adjusted the release rate. By 2025, major satellite operators were incorporating Elena's deorbit tethers into their spacecraft designs. SpaceX announced that all future Starlink satellites would carry tethers for end-of-life disposal. Amazon's Project Kuiper followed suit. The space insurance industry offered premium discounts for satellites equipped with tethered deorbit systems. The success of debris removal tethers opened the door to more ambitious applications. NASA's SwarmWorks program began testing tethered orbital tugs, spacecraft that could rendezvous with satellites, attach tethers, and then use electromagnetic forces to boost their orbits or move them to new positions. These space tugboats could extend satellite lifespans and enable orbital recycling of expensive spacecraft components. Elena was promoted to Chief Technology Officer of ISEC in early 2026, tasked with leading the most ambitious engineering project in human history, the construction of Earth's first space elevator. The project would require a tether 100,000 kilometers long, longer than the distance from New York to Tokyo, wrapped around Earth's equator 4 times. The engineering challenges were staggering. The tether would experience enormous stresses from its own weight, wind loads at various altitudes, and the gravitational effects of the moon and sun. It would need to withstand micrometeorite impacts, space radiation, and thermal cycling from -200 C. Most challenging of all, it would need to be manufactured and deployed without a single catastrophic failure. Elena's team chose a location on the equator in Ecuador, taking advantage of the country's existing space launch facilities and the minimal wind conditions at the chosen altitude. The space elevator would begin with a satellite in geosynchronous orbit, 35,786 kilometers above Earth. From this anchor point, 2 tethers would be deployed simultaneously, one extending downward toward Earth's surface and another extending upward into space to provide the necessary counterweight. The construction process would take 7 years and require unprecedented international cooperation. The upward tether would be built first, extending 64,214 kilometers beyond geosynchronous orbit. To balance the gravitational forces acting on the downward portion, automated construction robots would travel along the growing tether, adding new sections of graphene cable and monitoring structural integrity. The downward tether presented greater challenges. As it extended toward Earth, it would pass through regions of increasing atmospheric density, potentially causing it to oscillate or break. Elena's team developed a novel solution. The tether would be constructed in sections with built-in damping systems that could absorb wind-induced vibrations. The first major milestone came in late 2026, when ISEC successfully manufactured a continuous 1,000-kilometer length of single-crystal graphene tether, the longest ever produced. The material demonstrated tensile strength of 63 gigapascals, more than sufficient to support the loads required for space elevator construction. Quality control revealed no defects along the entire length. Public reaction to the space elevator project was mixed. Environmental groups initially opposed it, fearing unknown ecological impacts. Aviation authorities worried about interference with air traffic. Military strategists recognized the elevator as a potential target for hostile actors. But as the benefits became clear, dramatically reduced launch costs, unlimited payload capacity, and clean access to space, public opinion shifted. Economic projections showed the space elevator would reduce the cost of reaching orbit from $10,000 per kilogram to less than a 100-fold cost reduction, would make space-based solar power economically viable, enable massive space manufacturing facilities, and open space tourism to middle-class families. The elevator would pay for its $150 billion construction cost within 15 years. The first successful tether deployment test occurred in March 2027. A scaled-down version extending 10,000 kilometers was deployed from a geosynchronous satellite. The tether remained stable for 6 months, demonstrating that the concepts underlying the full-scale elevator were sound. Advanced computer simulations confirmed that a 100,000-kilometer tether could maintain structural integrity under all expected load conditions. Construction of the operational space elevator began in January 2028. The anchor satellite, built by a consortium including SpaceX, Blue Origin, and the European Space Agency, was the largest structure ever assembled in space. Weighing 2,500 tons, it contained the automated factories that would manufacture tether segments in orbit, using raw materials delivered by cargo rockets. Elena moved to the anchor satellite to personally oversee construction. Living in space for 2 years, she watched as robotic systems methodically extended the tether in both directions. The upward section grew at a rate of 100 kilometers per day, while the downward section advanced more slowly at 50 kilometers per day, due to the need for careful atmospheric testing. The most dangerous phase came when the downward tether reached the stratosphere at 50 kilometers altitude. Wind shear and atmospheric turbulence threatened to snap the impossibly thin cable. Elena's team deployed a network of stratospheric balloons equipped with stabilizing equipment that could dampen oscillations and guide the tether's descent. Technical challenges emerged regularly. Micrometeorite impacts severed tether segments, requiring the deployment of repair robots that could splice new sections. Solar radiation degraded the graphene surface, necessitating the development of protective coatings. Lightning strikes during thunderstorms induced dangerous electrical surges that had to be grounded safely. The breakthrough came in September 2030, when the downward tether successfully reached Earth's surface at the Chimborazo base station in Ecuador. For the first time in human history, a continuous physical connection existed between Earth's surface and space. The tether was so thin, just 1 meter wide and a few micrometers thick, that it was nearly invisible to the naked eye, appearing as a faint line reaching into the sky. Elena stood at the base station as the first test payload, a 100-kilogram satellite, began its journey to orbit. The climb took 14 hours, powered by a simple electric motor that rode magnetic rails along the tether. At an average speed of 200 kilometers per hour, the payload reached geosynchronous orbit, using less electricity than a typical American home consumes in a day. The successful test triggered a global celebration. Stock markets soared as investors realized the transformative potential of cheap space access. Space companies announced ambitious plans for orbital manufacturing, asteroid mining, and interplanetary missions. Tourism operators began taking reservations for space elevator rides, with tickets priced at $50,000 for a journey to orbit. But Elena knew the real revolution was just beginning. The space elevator was designed to carry payloads of up to 20 tons, enabling the construction of massive space-based projects that had been impossible with rocket technology. Solar power satellites, each capable of generating gigawatts of clean energy, could be assembled in orbit and deployed to geosynchronous orbit. The elevator also made Mars missions economically feasible. Instead of using expensive chemical rockets, spacecraft could climb the elevator to escape velocity and then use ion propulsion for the journey to Mars. The cost per kilogram to Mars dropped from $100 million to $1, making large-scale colonization possible for the first time. International cooperation became essential as demand for elevator access exceeded capacity. ISEC established a global consortium that included space agencies from 30 countries. Traffic control systems managed the flow of payloads, ensuring safe separation between climbing vehicles. Emergency protocols dealt with tether breaks, allowing sections to be isolated and repaired without shutting down the entire system. The environmental benefits were enormous. Rocket launches, which had contributed significantly to atmospheric pollution and ozone depletion, became largely unnecessary for routine cargo missions. The space industry's carbon footprint dropped by 95% as clean electricity replaced chemical propulsion for reaching orbit. By 2032, the space elevator was handling 1,000 tons of cargo per day, transforming the global economy. Rare earth elements mined from asteroids began arriving on Earth, reducing pressure on terrestrial mining operations. Space-based manufacturing produced ultra-pure crystals and advanced alloys impossible to create in Earth's gravity. Orbital habitats housed 50,000 people working in space-based industries. Elena, now 41 and director of ISEC, oversaw the construction of 3 additional space elevators. The second elevator, completed in 2034, was built from the Pacific Ocean using a floating platform anchored to the ocean floor. The third elevator, located in Africa, specialized in launching missions to the Moon and outer solar system. The fourth elevator, built in the Indian Ocean, focused on commercial satellite deployment. Each new elevator incorporated lessons learned from the first. Advanced materials included self-healing graphene that could repair micrometeorite damage automatically. Smart damping systems used AI to predict and counteract atmospheric disturbances. Redundant safety systems ensured that elevator operations could continue, even with multiple component failures. The Space Elevator Network enabled unprecedented projects. A lunar space elevator, anchored to the Moon's L1 Lagrange point, provided cheap access to lunar resources. Mars received its own elevator system, built using materials manufactured in the asteroid belt. The outer solar system became accessible to routine cargo missions, as payloads could be boosted to escape velocity cheaply. Elena often reflected on how profoundly the world had changed. The space economy now represented 15% of global GDP, employing 200 million people in space-based industries. Energy was abundant and clean, thanks to space-based solar power. Raw materials were unlimited, sourced from asteroids and comets. The environmental crisis that had threatened Earth in the early 21st century had been solved by moving heavy industry into space. But perhaps the most significant change was cultural. A generation of young people had grown up with routine access to space. To them, working on the moon or vacationing in orbital resorts was as normal as international air travel had been to their grandparents. Humanity was becoming a truly spacefaring civilization. Standing in her office aboard Space Elevator 1's geosynchronous station, Elena watched a steady stream of cargo containers climbing toward orbit. Each container carried components for humanity's next great project, an interstellar probe capable of reaching Alpha Centauri in just 50 years, powered by a solar sail manufactured from ultra-thin graphene produced in orbital factories. The space elevator had begun as an engineering challenge, how to build a cable strong enough to reach from Earth to space. It had become the foundation of human expansion throughout the solar system. Elena had helped transform humanity from a planet-bound species into a civilization that spanned the cosmos. The invisible highway to the stars stretched above and below her, nearly lost against the black of space and the blue of Earth. But its impact was visible everywhere, in the bustling orbital cities, the asteroid mining operations, the interplanetary cargo ships heading to Mars and beyond. Humanity had learned to climb before it could fly, and in doing so, had discovered that the universe was not a destination to visit, but a home to inhabit. The tether that had started as 20 kilometers of conducting cable on the International Space Station had grown into a network of space elevators that connected Earth to the infinite possibilities of space. And Elena Rodriguez, the materials engineer who had made it possible, had given humanity the greatest gift imaginable, a ladder to the stars that anyone could climb.